Hi, folks. I want to talk to you about a couple of strategies, a couple of things that will, a couple of elements that will pop up in or can pop up in certain situations when we deal with equilibrium and net torque analysis. So here's what we have. We have a plank. It has mass m and length L, some arbitrary length L. Let's see. This box has a mass m over 4 and is located at a distance L over 4 from that end of the plank, position shown. And this cable is located or holds this system up at a distance L over 3 from this wall here. And here's the wall, and here's a hingey thing, and here's like a pin through the, you get what I'm saying, right? This thing can pivot on that hinge. Yeah, dig. And this cable here holds everything nice and in equilibrium. So, what's the tension on the cable, and what force does the hinge exert? So, I'm going to draw a separate free body diagram, and I want to show you. I want to show you the way to handle a couple of things. Specifically, one of them is this: what's going on with this box? Because here's what there's a couple of things we got to deal with. One is, yeah, the box. So look, here's the box. I'm not saying the box is over here, but I'm saying that's the box. Let's model the box. Well, here's what happens to box. Or, yeah, sure. So let's call this M box G. And this is normal exerted on box by plank. Right? Yes, sure, good. Of course, we know cable, there's a tension on cable. Bink. Tension on cable. There is the weight of the plank, M plank G. The hinge thing. Oy, oy, oy. Well, here's what it's kind of hard to, something's going on at the hinge, probably. The hinge is exerting a force. I'm going to say like this. Maybe it's up. Let's call this, I'm just going to call it H, the force exerted. Oh, I don't know. What do you want to call it? It's a normal force, right? All right, fine. Let's call it normal on plank by hinge. And maybe it's up and maybe it's down. And maybe you're saying, what do you mean maybe it's up or maybe it's down? It's got to be fill in the blank. Well, it can be hard to know, or it can be hard to just pick. And I'll show you later how we'll know. So notice this is incomplete because look, we've got a force exerted on box by plank. Newton's third says, therefore, there must be a force exerted on plank by box. And it is a normal force, and this is a force pair. But what I'm going to typically do, and what you might typically want to do, is call this not a normal force, but call it what it's equivalent to, which is the box's weight. Yeah? So it might seem like we're splitting hairs and who really cares, but this is not actually a gravitational force acting on the plank. It's a normal force. That normal force happens to be the same size as it is the same size as the block's weight. So we can say that there is a force exerted at this location on the plank that is that big. Fair enough? Now, what people will do incorrectly, sometimes I hate to say, here's the wrong thing, but what people will do is they'll draw this and they'll say, okay, well, all right, I got I know there's this tension thing here. I know there's the weight of the plank here. And what they'll do then is say, okay, there's a force like this and like this at the same place. But these forces are not exerted on plank. What it seems like you're doing, people that do this wrong, is it seems like they're modeling the forces acting on the box, but this is a free body diagram for the plank, and so this ain't right. Particularly this part is not right. We only want to model forces acting on the plank. And again, this is actually not even the actual force acting on the plank. The actual force acting on the plank is a normal force, but it's that big, so let's just call it a force that big. Fair? Yes? And the reason I have this, you don't necessarily need to draw this, But the point of drawing this model of the box is to say, well, there's this force exerted on box by Planck, therefore there's an equal and opposite force exerted on Planck by box, and then we just sort of do a quick net F of the box to say how big is this normal force? Well, it's that big, so let's just call it that force. I know I'm repeating myself over and over, and maybe speaking fast is not doing you any real help, but that's a way to handle this kind of scenario when you have something sitting on a Planck. A different scenario might be, sidebar, might be like, all right, we've got a Planck thing like this, and there's something hanging off of it like this, right? Well, the actual force exerted on the Planck by that hanging thing, come on, yeah, is a tension force, right? But how big is the tension force? Well, it's the mass of that hanging object times g. It's not that the object's weight pulls down on the Planck, it's that the tension pulls down, but we just typically say that's the size of the force. Repetitive. I know. Fair? Fine. Okay, onward. Let's go ahead and do the analysis here now. Here's one big deal. A net F, I don't even know what direction these forces point. So a net F is sort of maybe not the way to go. So I'm not even going to bother writing a net F. I'm going to go right to a net torque. Right to a net torque. I hereby decree. And well, specifically because I don't know what the heck is going on here, I'm going to eliminate that force from my analysis by locating points of action of forces relative to that location. So there's an R to T, here's an R to M. Well, how about a R to the Planck? I don't know, sure. And here's an R. Uh-oh, not good. It's okay. Here's an R to the box. Yeah? Okay, so notice the direction that so this does something like that. This does something like that. This does something like that. So we've got some different directions of torque. Why don't we go ahead and call this way the positive direction? You just have to choose one. So I'm going to say there's a torque created by the Planck, by the Planck's weight. There's a There's a torque created by the Planck. There is a torque created by the box in the same direction. There is a torque created by the tension in the opposite direction. This system's in equilibrium. Yeah. We're looking for the tension force. So let's see. The torque by the tension equals the torque by the Planck plus the torque by the box. R to the tension times the tension. R to the Planck times, well, not times the Planck, but really times the Planck's weight, plus R to the box times the box's weight. The tension is all that stuff divided by R to the tension. So now let's start to maybe do some substitutions. So T is R to the Planck. Well, that's right. Look, remember the Planck has a length L, so R to the Planck is L over 2. And M Planck is called M. Okay, R to the box. Now look, I gave you this dimension, but we're locating our forces, points of action relative to left end, so that is 3L over 4. And the box's weight is big M over 4 times G. I'm going to divide by this R to the tension, which was L over 3. And now it's algebra. Okay? So let's see, we got like a 1/2 LMG plus 3, 3/16 LMG divided by, oh look, divided by L divided by 3. Yeah, divided by, the same as multiplied by. Holy mackerel. So what's a half? Oh, look. We've got a L in both of those terms. So 1/2 is 8/16 plus 3/16. 8/16 plus 3/16 is 11/16. Okay. So 33. So this tension is 33/16 mg, a little bit more than twice the weight of the plank. All right, sure, makes sense. I guess, right? Fine, good. Okay. So now, a typical problem like this says what you can do is first a net torque, and then you should be down to a single unknown, right? Our unknowns in the beginning here were, come here, were what's this tension, what's going on here, 2 unknowns. Right now we know the tension. There's only one unknown thing, and it's what's going on at that hinge. So here's what I'm going to do. I'm going to say that a net F says that, well, tension minus M plank G minus M box G. Yeah, what do we do with the plank thing, right? Well, how about this? Let's just say plus, what do we call that? We call it normal on the, yeah, then let's call it that normal force. Normal on plank by hinge. All right, now, I'm calling it positive. I'm saying it's upward. I'm just sort of taking a shot in the dark. All right, so the tension, what was the tension? The tension was 33/16. This is probably not going to be fun. 33/16 mg minus, well, this was the plank's mass is m. The box's mass is m/4 plus n equals 0. And notice there's no r's here because this is a net force analysis. So all we have to do is quite literally look at the size of the forces, and it has nothing to do with what their points of action are. Okay, so let's see. Here we got a, here, watch. Let's see. Normal on plank by hinge equals, let's see, mg plus m/4g minus 33/16 mg. Oh boy. I can already tell that our answer is going to have a certain sign. Okay, otherwise we'll factor out all the mg's. We got 1 here, we got a quarter here, and we have negative 33/16 here. So 1 1/4 minus more than 2. So normal on plank by hinge is negative some fraction, which I don't care about. I mean, it's not too hard to solve, right? This is 5/4, which is 20/16 minus 33/16. All right, fine. It's negative 13/16 mg. Now, this negative means, right, this negative means I said the thing pointed up. This says, you're wrong. It points down. So it's kind of neat, right? So we say that, I mean, the best answer here is that the normal on the plank by the hinge is, 13/16 mg downward. So you'd think that, well, I mean, hinge holds thing up, right? But no, the hinge actually has to exert a downward force. Because look, watch, yeah, of course it does. We didn't even need to do any of it. I mean, to find the size of it we did, but look, if we do a net torque about that location, of course, look, there's torque this way, torque this way. If there's going to be an equilibrium condition, an equilibrium has to be true about any axis, or about any chosen origin around which to locate points of action of other forces. this force, yeah, has to go this way, right? We've got this green torque, this pink torque. We've got to have this counteracting torque by that normal force in order to keep this thing in equilibrium. I'm surprised it's only that big. I might have made an error somewhere. I wonder if I did. But what's nice is this, we didn't even have to find the size of it in order to know the direction of the force that this thing exerts. If we choose an origin carefully, then we can say, oh, of course, these are two clockwise torques. There must be a counterclockwise torque by that normal force, so it must point downward. Mustn't it? Oh, it must. Can it really only be that big? Yeah, I guess. Because this, yeah, I can justify. Okay, buddies. So maybe a couple of things. One of which is how do you handle these, things like this? Well, that was what this whole discussion was about. Let's model that object itself, and then typically what we'll do is end up talking about how big is the force exerted on the plank by that thing, and make sure we don't say, well, I'm drawing both the plank and the thing. That's what this wrong free body diagram typically is. You're modeling not the plank, but the plank and the object on it, except you're still doing it wrong because there's also this, whatever. Yeah, so no up and down force at same location. Those are the forces exerted on the plank. And then secondly, right, what force does two ways to do it. If we want to actually find the force, typically our second unknown you can find via a net force analysis. If the question was what direction is the force exerted on the plank by the hinge, if we choose an origin carefully, we can just tell that this force must be downward in order to create equilibrium. Fair enough? All right, buddies.